In this video, we're going to talk about solving exponential and logarithmic equations, and we're going to be using the order of operations in reverse, just as we have in many other units. So, as you know, when you simplify, you start at the grouping symbol, then you do exponents and logarithms from left to right, multiplication and division from left to right, and addition and subtraction from left to right, but never mixing these steps up and going in this order. When you solve, you obviously will add or subtract to eliminate anything around or outside of, in this case, the exponential or logarithmic functions. You will then multiply or divide to get rid of coefficients on the exponential or logarithmic functions. And then it's kind of interesting. You use a exponent to eliminate an exponent, you'll use a logarithm of the same base. And to eliminate a logarithm, you use an exponential function of the same base. Those are inverse operations. And then you will use, if there's anything inside of the exponential or logarithmic function, you will use order of operations in reverse again for everything in the grouping symbol. It's also extremely important to check your extraneous answers. And I'm just going to show you two graphs to help you understand why this is so important. So if you have an exponential function, something like y equals 2 to the x, that graph looks like this. It kind of looks like a slide going upwards, and we've already talked about that picture. In this graph, the domain is negative infinity to infinity. What that means is this graph, for every input, you have an output, okay? But the graph of a logarithm, I'll just say log base 2 to show you what it would look like. It is the inverse, and so it would reflect over the line y equals x, and it would actually look like this. And the reason that's important, very important, is the fact that there are no values over here in the negatives. In fact, the domain of all logarithms that have not been translated or transformed is 0, non-inclusive, to infinity. And we'll talk more about this, but this domain restriction of extraneous answers is extremely important for logarithms. For exponentials, there are some extraneous answers, but for logarithms, clearly half the graph is missing. So that's obviously going to be a bigger deal. To also remind you, we do have these important exponential and logarithmic rules that will play a part in solving equations. For instance, if you have a base that is the same and you multiply those bases, you will add their exponents. Those exponents could have variables in them, so you'd have to combine like terms. If you have the same base with division, you would subtract, which again, you would have to distribute the negative sign and combine like terms. If you raise a base to a power and then another power, you will multiply, which may involve distributing or boxing or using the FOILing. So for logarithmic function, it actually works in reverse. Logarithmics are the same base that are multiplied inside the parentheses, become addition of two separate but the same base logarithmic expressions. Same thing for division, but it's subtraction. Remember that this really means that it has a negative exponent on up here. So that's, just reminding you that that's how that works. And then the most forgotten for some reason is, in my opinion, the easiest, which is if you have a logarithm of something that's an exponent, you can actually move that exponent to the front and produce multiplication. Remember, it's this rule in reverse. So if I have an exponent, I'm going to yield multiplication, as you can see. So in these rules, you can see the inversing happen. And that inverse relationship is really what solving equations is all about. So in these examples we're going to start with, we're going to be solving exponential functions. But in order to solve an exponential function, we're going to need to use a logarithm. And the reason is we're doing the order of operations, right? Good old GELMDAS. And as we start at the bottom, everything is going to feel very normal. We're going to be getting rid of addition and subtraction, and then multiplication and division. And then we're going to get rid of the exponent base with a logarithm. So the first thing I see here is there's actually nothing to add or subtract, so I get to skip that. But then there's multiplication, which means I have to then use the rule for multiplying the same base, which is what we were talking about here. If I have the same base, I take those two exponents and I add them together. So in this case, my same base is 5, and my m, my first one, is x minus 3, and my n is this one. So I'm going to write that down. I like to use parentheses to make sure I keep things straight, especially if I were subtracting, right? But in this case, I'm just combining like terms. Math is just always repeating things you already know. Like you already know how to complete like terms from Algebra 1. Same thing, only different. So I'm combining those like terms in an exponent right now as opposed to as its own problem. This doesn't do anything, so it just drops down. And so I've completed my multiplication step in a way that maybe is a little bit surprising, but it's done. And now the question is, how do I get rid of 5? Like, I need to solve for x. I can't just like start solving stuff. I have to have a reason to get rid of the 5. And so if you have 2 to the x, the way you get rid of that is log base 2. If you have 3 to the x, the way you get rid of that is log base 3. And if you have 5 to the x, big surprise, you would use log base 5. Please keep in mind, if you have 10 to the x, you would be using just regular old logarithm, because log without a base is actually log base 10. And so the effect here is that in all of these problems, these things cancel, leaving you with just the exponent. So if I go back and look at this problem, I'm going to log base 5 to cancel this and drop this exponent down. I do the same thing to both sides. So it simultaneously drops them both down to ground level, so to speak. So once I do that, the question is, well, how do I solve it? I just, as I mentioned earlier, this is technically in a grouping symbol, technically in a parentheses. And so once you drop it down, the parentheses is gone, and you start at the bottom of order of operations, and you just start with addition again. So I'm going to subtract 1 on both sides. Okay, and then I'm also going to subtract 3x on both sides. I'm just literally solving this problem as if I was back in Algebra 1. And so 2 minus 3x is negative x. These cancel, and this comes out to negative 5. And then I do my division step, divide by negative 1 on both sides, giving me x equals 5. All right, so that is my answer. The question is, does it work? You can always check this by just plugging it back in. And I mean, we could easily do this, just in our brain, right? If I put 5 right here, I would have 5 minus 3. So this would become 5 squared. And then I want to multiply that times 5 in here, which would be 5 to the 9th power. And so this comes out to 5 to the 11th power. I don't need to know what that is. It's some huge number. I don't really need to know what it is. So the question is, will I get the same thing if I plug it in here? So here I have 5 to the 3 times 5 minus 4, and so that's 15 minus 4. Yeah, I get 5 to the 11th. So that is, in fact, the solution. Okay, so the very next problem, oh man, boom, put an E in there. We should not be afraid of E. The way you get rid of E is to use ln, right? So over here, we're talking about these canceling and these canceling and these canceling and these canceling. And the way you get rid of E to the x is you would use log base E, but log base E is called ln. Okay, so it's the exact same thing as over here. In fact, you don't even need to know what E is. E is 2.718. You don't need to know that. You just need to know that how to cancel it, right? So we're just going to do the same thing. We're going to start at the bottom of the order of operations. We're going to add 2 to both sides, okay, because that's the first thing we do, add or subtract. And when I add that, I get 18. Everything else drops down. And of course, this inverse operation I did here will cancel. And so now I've done addition and subtraction, so I'm going to do multiplication and division. I'm going to divide by 3. Okay, no big deal. Everything seems normal. It is. Same thing, only different. Over here I get 6. And here I'm going to ln. And so ln will cancel E. And over here, ln does not do anything to 6. It just is ln of 6. Think of this, okay, as if you were trying to take the square root of 6. It wouldn't do anything. You wouldn't be afraid to just write down the square root of 6. So this is sort of like that, same thing, only different. I would need to figure out what that is in a calculator, which I'll show you in a second. So this thing right here is just going to drop down after its base is canceled. And then I will subtract that 2 on both sides because I'm, did the grouping symbol, boom, back to the bottom of order of operations. And so we get x is equal to negative 2 plus ln of 6. Now, where did the plus sign come from? These are not like terms. So if you had an x and a 6, how would you combine them if they weren't like terms? You just put a plus unless one of them were negative. So I have the negative on the 2 there. And so that just comes out to negative 2 plus ln of 6. Now, many students will say, how come you didn't say ln of 6 minus 2? And the reason is not everybody writes those parentheses down. So if I wrote ln of 6 minus 2, the question is, do you mean ln of 6 minus 2 or do you mean ln of 4? So we always put that integer in the front so there's no question about what it is. So taking a look at what this answer means, if I were to type it into the calculator, okay, I would just type in, right, -2 plus ln of 6, and it's just this crazy decimal. So what in the world does that decimal mean? If, oh, by the way, where did I get ln from? It's not there. I literally just typed it in. I mean, you can maybe find it under function, but you can just type ln with the keyboard in. So if I say x equals this, and I hit enter, and I type in the left side of the equation, 3, by the way, e, the computer understands what e is, and then I raise it to this exponent. I find it easier to type it out, highlight it, and then hit the exponent button. It seems to work better. So just keep that in mind. And then if I hit -2, look what it says. It says if you type in this crazy irrational number that's ln blah, 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 when that gets plugged into here, you get 16. And that's pretty powerful to understand how simple this process is and how routine it is and consistent with other math problems. So looking ahead at some other things, like what do you do when the bases aren't the same? And you might have wondered that. You might have been like, well, what do I do if that's a 4? What do I do if I have like a 2 to the something over here? Well, what you do is you try to make them have the same base by just kind of thinking about your exponents, right? So you're going to rewrite this with a common base of 5. What do I mean by that? Well, 125 is actually 5 to the 3rd power. And 5 is, of course, just 5 to the 1st power. So now I have the same base, which means I'm going to be able to use the same base logarithm. So you put this in a parentheses, okay, because, this thing, right, think of the fact that I'm changing that. So I want to put that in a parentheses to make sure I don't mix up what I changed. And then over here, this one's not changing. If you want to put it in a parentheses, it's not like that's a bad thing, but that one didn't change. And so what I'm going to do is I'm now going to use log base 5, right? So log base 5, and then over here I'm going to log base 5. And so these will cancel, and it will drop down to everything you see here. So the 3 did not get canceled. It's dropped down. And then the x minus 3 drops down. And then the 5 cancels, and then over here the 3x minus 4 drops down. So here, if I distribute, I'm going to get 3x minus 9, just because you have to get rid of that parentheses before you do anything else. Because remember, once we get rid of this exponential step, we're now worried about grouping symbols again. That's why I have to make sure I distribute that. And then from there, I start at the bottom of order operations again. And so what I'm going to do is I'm going to add my 9, right? Getting rid of my addition and subtraction step. And then I'm going to subtract 3x on both sides. And I just wanted to review that things you learn in Algebra 1, they never go away. So here, this cancels, and over here I get 0, right? 0 is equal to 5. And you may remember what that means. That is the empty set, or otherwise known as no solution. Keep in mind that empty set in an Algebra 2 class, because this is the Algebra 1 way to say it, could be written as literally a set of nothing. So all of these things basically means there's no answer, because there's basically just the x's are gone. So if the x's are gone, there's no way to find an answer. And plus 0 can never equal 5. You may remember that solving technique from Algebra 1. So this problem had no answer. It means there's no input here that I can put in here and get the same thing on both sides. All right, so same idea over here. We're going to try to rebase this with a common base of 3. So this side's really easy. It's just 3 squared. Go ahead and put that in a parentheses. Kind of like, you're saying, what is 9? 9 is 3 squared. And then we have x minus 5. But then over here, what is a third with a base of 3? That's 3 to the -1, right? Because -1 would mean I put this thing on the denominator. So it actually goes both ways. You can rewrite a fraction as an integer with a negative exponent. And then you put the x plus 10 here, and then you're going to base 3 this. That's how we say that normally. So I'm going to log base 3. And that's going to cancel the bases. Everything else is going to drop down. So the 2 and the x minus 5 drop down. Over here, the -1 and the x plus 10 drop down. And then I distribute, right? Bloop, bloop. and then bloop, bloop. And so I get 2x minus 10, and then it's just like I'm back in algebra 1 yet again. So I'm going to add 10 to both sides. Now over here, I did this on purpose. I do get 0, but it's not really a problem to get a 0 in this for the integer. It's a problem to get a 0 for the variable, right? So this cancels out and this cancels out. This will add up to 3x, and over here, this comes out to 0, and when I divide by 3, I get my answer is 0. So I guess the question is it a problem for your answer to be 0? And the answer is no, as long as it works. So if I take the 0 and I plug it back into here, I would get 9 to the negative 5th power. Okay, so let's see if I get the same thing here. When I plug it into here, I get 1/3 to the 0 plus 10, which means I have 1/3 to the 10th power. And the question there is, are these the same thing? And that's a weird question, and it's because we changed the base. They are, in fact, equal. Let's take a look at a calculator here. So if I do 9 to the negative 5th power, that is this problem in scientific notation, and if I do 1/3 raised to the, oops, got to make sure I use my parentheses correctly. So if I raise that to the, this is a little tricky. So 1/3 in a parentheses, 1/3 in a parentheses, and then raise that to the 10th power, you can see I actually get the exact same thing. And of course, you could have also checked this, instead of checking it this way, you could have checked it by saying x is 0. What is 9, right, raised to the x minus 5? Oops, you got to be careful with typing that in. So I do x minus 5. I highlight and then exponent. Notice I get the same number you saw earlier. And then if I take 1/3, okay, and again, I'm just going to type the exponent in and then tell it to make it an exponent. You can see that I said, hey, x is 0. Can you evaluate this and this at 0? Notice I get the same answer both times. It is not a fraction. You know, if you ever click that, it won't let you have it. It won't let it work. So we really just got to make sure that we're solving things using the same process we've always been using, which is the order of operations in reverse. We have to do it more than one time quite frequently. And we have to make sure we check our answers and understand what our answers mean. All right, so now we're going to do solving logarithmic equations using the exact same process. The difference is when I get to this exponent logarithm step, I'm going to need to use an exponential base instead of a logarithm because I already have a logarithm. So again, I'm just going to add or subtract. In this case, I'm going to subtract 7. You know, pretty routine. I get 3 here. Everything else just drops down, waiting for its turn. Okay, there is nothing to add or to multiply or divide, so I get to skip that step. I'm now going to get rid of the logarithm by doing the exact reverse of what I did earlier. So, for instance, if you have a log base 2 of x, the way you get rid of it is you raise it above 2. If I have log base 3 of x, I raise it above 3. If I have log of x, I raise it above 10. And if I have ln of x, I raise it above e. So in this case, to get rid of this, I raise it above 3. It's called basing, right? I base the logarithm to cancel it out. But over here, you have to understand that this is actually 3 to the 3rd power, which would be 27. Everything else just drops down, and then I subtract 1, and the answer is 26. So how do you know it's the answer? It's very important to check your stuff. So you take this answer and you plug it into here, and I want you to think very carefully about this. If I put 26 in there, I would get log base 3, okay, of 27, because x plus 1 plus 7 is 10. And so remember what we learned in the first unit. This really means 3 to what power is 27? Well, 3 to the 3rd power is 27, and if you add 7, you get 10. It's important to know how logarithms work. Again, how did I do that? 3 to what power is 27? 3 to the third power, the 7's still there, 3 plus 7 is 10. All right, so what do I do when I have an ln? I do not freak out, right? What I do is I subtract 1 on both sides, and I just do what I've been doing since the beginning of the school year. I get a 6 here, I cancel this out, I drop this down, okay? And then what I'm going to do is I'm going to divide by 2, giving me 3. And that'll give me ln of x minus 3. And then I'm going to e both sides. I'm going to e here and I'm going to e here. This will cancel, giving me x minus 3 equals e to the third power. Again, sometimes I tend to go back to my cursive. Keep in mind that this L thing is really a cursive E. Can't help my training when I was a kid there. And then we add 3 to both sides. And when you add 3 to both sides, you end up getting x is equal to 3 plus e to the third power, which is very hard to check, obviously, right? So what we're going to do is we're going to, go to a calculator, and we're going to say, hey, I think the answer is 3 plus e to the third power. And then we're going to type in the left side of the equation, 2 ln parentheses x minus 3 outside of the parentheses plus 1. And as you can see, this is just old stuff, I'll get rid of it. You can see that it says, hey, that equals 7. So I did solve it correctly with this weird answer, okay? All right, so let's keep going. What do I do when I have to add logarithms? Well, I got to remember to go back to this rule. When I add logarithms, it means I multiply them. So what that means is, on this problem, is in order to solve this problem right here, I have to first write down one single logarithm, and then remember that inside that logarithm, I'm going to multiply these two together. And evidently that will equal 1. Okay, so when I multiply this together, I'm either going to FOIL or box, or hopefully at this point you understand that you're just basically adding these two with an x and then multiplying them with an integer. So that will come out to x squared plus x minus 6. And of course, this equals 1. So how do I get rid of log base 3? I base 3. But I have to do it over here. And remember that that really means 3 to the first power, right? So this mess is 3 to the first, which is just 3. This part just drops down. So what do I do now? I remember that I'm in Algebra 2, and we did a unit on quadratics. And so I would set this equal to 0 and use the zero product property. So what I'm going to get here is x squared plus x minus 9 is equal to 0. And then I'm going to ask myself, does 9 factor? It does, but unfortunately that would make me have -8. So sometimes I've got to use the quadratic formula or even completing the square to do this problem. With this little bit of stuff, I'm probably going to complete the square, even though it's fractional. Let's see. So I add 9 to both sides, and then that gives me a space. So x squared plus x plus a blank is equal to 9. To complete the square, I take half of b, so 1 is b, divided by 2, and square it, which gives me a fourth. So I'm going to put 1/4 here, and I'm going to add a fourth here. Okay, so to combine like terms here, I would need to turn the 9 into a fourth, which would be 36 fourths. So this comes out to 36 fourths plus 9 fourths, which is 37 fourths. This right here will factor. It always factors into whatever I have here. So I think this is part of the reason some students have trouble with completing the square. They don't understand the answer is actually already on their paper. So there you go. And then what we're going to do is we're going to take the square root of both sides. Make sure you take the square root of the top and the bottom separately. So we get x plus a half is now equal to plus or minus the square root of 37 over 2, because the square root of 4 is 2. And then I subtract a half on both sides, and I get -1/2 plus or minus the square root of 37 over 2. Again, what I did in my last step is I subtracted a half. So you could type that thing into a calculator. The main thing I want you to realize is the negative answers aren't going to work. Because a negative answer, if put into here, would produce a negative logarithm on the inside. And logarithms can never be negative on the inside. Their graph looks like this. So there are no negative logarithms. If this is what a logarithm looks like, you can see there is no domain that would produce a negative answer. So the question is, do either of these answers work? Well, here are the answers. Negative 1/2, right? So negative 1/2 minus the square root of 37/2. There's no way that works. And so then we also have, because it's just a negative and a negative, we also have negative 1/2 plus the square root of 37/2. And to see if that works, I sort of need to know, is this answer positive? Because if it's negative and I put it into here, we have a problem. So let's see. I'm going to go into here and we're going to see what this actually comes out to. So let's see, let me get rid of this old stuff and that other problem. So negative 1/2 and then plus the square root of 37, turn that into a fraction, over 2. So I get 2.5, which is a good thing, because that answer, again, if I put that into here, will be okay. And I know that's a lot of conversation because you could have just done this and then typed in, but you can't type in log base 3. So there's the problem. You do sort of have to understand things sometimes. There is no way to type in log base 3 because see, it thinks you're multiplying or it thinks you're taking the log of 3. So you have to really watch out for, is your answer negative in a logarithm? So the negative answer doesn't work, but the positive one does. Okay, so here's our last one. What do we do when we subtract a logarithm? So subtracting a logarithm means log and then basically draw a fraction, right? Because minus of a logarithm means denominator. So this part here stays here, and then this x goes in the bottom, and this equals 2. I want you to notice that there's some algebra that can be done here now using a GCF. So I'm going to do that algebra before I do my next step because I have a parentheses, and anytime there's a parentheses, like here, the parentheses said multiply. Over here, the parentheses says, hey, look at this and see if there's something you can take out. So I can take out a 3x, and I'll get x plus 2. And then this x right here will immediately cancel with this x. So my next step is to just remember I am in Algebra 2, and all the Algebra 2 that I've learned is going to come back just, at any given time. So I end up with this inside, and the denominator cancel. So now the next question is, how do I get rid of the log? Well, I'm going to base 10 if a base is not given. So over here, we have a base 10. And so this will come out to 10 squared. That's what that's really saying, which actually is 100. Okay. And then this, of course, I guess I got to put that back together, right? So I actually get 3x plus 6. Sorry, I put the 6 down first on accident. So 3x plus 6, and then I would subtract 6 on both sides, giving myself 94, right, because I subtracted 6. And then I would divide by 3 to get my final answer, okay? So I don't even know if that reduces, so let's just double check, okay? Doesn't appear to share a multiplication table. So 94 divided by 3. It's 31 1/3, but that's not actually going to reduce because if I toggle that, you see that that's the answer. So what does that answer mean? So luckily, it's not negative, so that's good news. Luckily, I can actually type that into the calculator, and the reason I can type it in is because it's log. So anytime you type something into the calculator, it thinks you mean log base 10. Okay, so if I type this, it's taking log base 10 of 3. So luckily, if you have an ln or a log problem, you can actually double check it like this. Store that, and then type in log parentheses 3x squared, and then plus 6x, and then on the outside, you're going to type in minus log of x. Now, you might say, where are you getting that log function from? I'm literally typing log into the calculator. So you can see that if I type in 94/3, and then I type in the original problem, that it comes out to 2, which is exactly what it's supposed to. So check, that works. what is the overall thing we have to remember? We have to remember that basing a logarithm will cancel the logarithm, but I have to actually evaluate it on the other side. And I have to remember that negative answers have to be checked. And, I'm sorry about throwing the quadratic equation in here without a factorable expression, but we can't get away from techniques that we've learned. And that's why I brought that up. I mean, obviously, sometimes this will factor. Imagine this was a 2. Sure would have been a lot easier. But my point is that we can't get away from factoring GCFs out. We can't get away from the quadratic formula or completing the square. And now we have to add in the idea that I can't have negative answers in logarithms. It seems like a lot, but it's actually just a lot of review. So now that we know how to solve both exponentials and logarithms, we need to remember how to do inverses as well. I remember to find inverse, what you're going to do is you're going to take f of x, which is y, and x, and reverse them. You make the domain the range, and the range the domain. So f of x becomes x, and this x would become y, but everything else would then just drop down. And then your job is to find the inverse. Now, the interesting thing enough is this actually is the inverse. You can't graph it, you can't solve it, it's not very useful in this format. So that's where we're going to, of course, reverse the order of operations, just like we normally would. And the exponent and logarithm step is the new step for this unit. So we're looking for addition and subtraction right now, so we obviously have to add 3 to both sides. Once we do that, we're then going to be looking for a multiplication or division step. And this is where it becomes really critical to understand this parentheses on exponentials, because some students will try to divide by the 2 or maybe even combine these. That 2 is the base and cannot be eliminated without a logarithm. So our next step is to multiply by 4 to cancel out the 1/4. But just make sure when you do it over here that you actually distribute it. Okay, so just make sure you don't divide by a base. Bases you can't divide by them. Logarithms get rid of bases. And then make sure that when you do multiply or divide on the other side that you distribute that value. All right, so now we're going to we've done the first 2 steps, addition and subtraction. We did multiplication and division. We're now going to use a logarithm to get rid of the exponential base. So we're going to log base 2 here. And then when we log base 2 here, we don't distribute this. We just put all of this into a parentheses. All right, so we have log base 2 of 4x plus 12 is then equal to, remember, log base 2 and base 2 cancel, dropping down the exponent. And so now we have this grouping symbol that we have to do, and we just go from grouping symbol, we go right back down here to add or subtract, and it's just make sure when you subtract that 2 that it's outside of the parentheses. Now once I do that, I have to make sure that I put this in proper notation, that I don't accidentally combine things that don't combine, right? So that 12 and that 2, they don't combine. One is in a logarithm, one is not. And our last step is to then rewrite it using the inverse notation, because this y right here, notice there was never a y in the problem. The y is just easier to write down than f inverse the whole time. So just make sure at the end you then correctly write down the inverse notation for that problem. All right, so to remember what a logarithm, what an inverse does, is if I were to put a 1 in here, I would get an answer, okay? And that answer that I inputted here would then be the output here. It changes the inputs, makes them the outputs, changes the outputs, and makes them the inputs, okay? So let's take a look at what happens with a logarithmic problem. Same deal, we are going to switch x and y. This will become x, and the x will become y. And once I do that, it's just the same reverse order of operations game that we just played, minus a slightly different thing to do in this step. So I'm going to add 5 at the bottom of the reverse order of operations is addition and subtraction. All right, and then a lot of students, they kind of forget about negative signs. It really means -1. So you can actually multiply or divide by that -1. Technically, it's multiplying, so I like to divide. which means you would divide each of these, right? Don't forget to distribute your multiplication or division. So we get negative x minus 5 is equal to, this would cancel, so ln of y plus 2. And then what we're going to do here is we're going to base this. So if this were a log base 3, we would base 3 it. If it were log, we would base 10 it. ln has a base of e, so we're going to base e it. Okay, so sometimes I write cursive e's, they look like L's. Sometimes I write regular e's. When I was a kid, we still learned cursive, so just realize that that e thing is a cursive L. Okay, so we end up getting e to the negative x minus 5, okay, is equal to, these will cancel, is equal to y plus 2. And then to solve for y, we're going to go to grouping symbol, back down to the bottom. So we now subtract 2 on both sides. Just make sure that you don't put that in the exponent. It would not be in the exponent. It would look like this. E to the negative x minus 5. Then minus 2 is down here. It's going to be identified later as the k value. Remember back when you did transformations and translations, this would be h and this would be k. And just don't forget that we have to rewrite this in the right notation as well. Can't really use y. There was no y. Y is a placeholder. Again, you really could, instead of using y, you could write f inverse in every step. It just gets tedious, so typically we just write y. All right, and there's that inverse. So inverse is not a difficult process. It follows the same process as solving, but you have to remember to switch x and y and then solve for the new y. And don't forget to change it to f inverse, because that's what y really represents in both of these examples.